This question is about acids and bases. 4.1, calculate the pH of a 0.150 mole per decimeter solution of ethanoic acid at 25 degrees. Give your answer to 2dP. That's very important here. We often miss this, and that will cost you a mark. For ethanoic acid, Ka is 1.74 times 10 to the minus 5 mole per decimeter at 25. You need to be able to write the expression for Ka, and just like Kc or Kp, it is products over reactants. So what are our products? What are our reactants? So if we have ethanoic acid here, what I'm doing is just showing you that ethanoic acid will break down to release hydrogen ions and ethanoate ions, okay? Just like this. So you're probably all familiar with that. Ethanoic acid, reversibly, because it's a weak acid, we use that symbol, breaks down into hydrogen ions and ethanoate ions. So if we want to write the Ka expression, normally if it's Kc or Kp or Ka, any constant, you're going to write the products over the reactants. So normally you're going to say, okay, the concentration of the hydrogen ions times the ethanoate ions, and we're going to do that there we go. This is taking forever. Over the ethanoic acid concentration. However, there is another simplification for this rule as well. So, because the number of hydrogen ions released is going to be equal to the ethanoate ions, so for every one molecule of ethanoic acid that breaks down, it will release one hydrogen ion and one ethanoate ion, which tells us that these two have to be equal. Then we can simplify this even further, and we can write this as Ka is equal to the hydrogen ion concentration to the power of 2 squared, and we can do that over the top of the ethanoic acid concentration. Notice the concentration, we're using square brackets for the concentration. Okay, brilliant. So in this question, you've been asked to calculate the pH. That is the most important part of this question, is actually what are you going to do? And that is to calculate pH. Now, whenever you see pH, they want you to calculate that, we have to understand that pH is equal to the minus log of the hydrogen ion concentration. So we need to find the H plus concentration. And so in order to do that, we need to rearrange this to make hydrogen ions the subject of the equation. So go ahead and try to do that. And if you do that successfully, what you should get is that I've got to multiply the Ka and times that by the ethanoic acid concentration. So if I multiply Ka by the ethanoic acid concentration, and then what else do I need to do? Well, I'm going to need to square root all of this, because if I square root it, I get rid of the square on the hydrogen ions. So there you go. That's my rearranged equation. Square root the Ka multiplied by the ethanoic acid, and that gives me my hydrogen ion concentration. And let's go ahead and plug those numbers in. And so what you should do is plug in square root and then into your scientific calculator 1.74 times 10 to the minus 5, and you're going to multiply that by 0.150 mole dm minus 3, which is of course the concentration of the ethanoic acid, and that will give you your hydrogen ion concentration. And you should get something along the lines of 1.62 times 10 to the minus 3. Now, what you want to do next is find out the pH. So you press the minus button on your calculator. Don't do inverse log. Press minus, then the log, and then tap in the hydrogen ion concentration of 1.62 times 10 to the minus 3. So you want to do this. Minus log, and then get your hydrogen ion concentration, which is 1.62 times 10 to the minus 3, and then see what that gives you. Go ahead and do that now. Minus log 1.62 times 10 to the minus 3, and you should get roughly 2.79. In fact, you'll get 2.79 and some various other numbers, but of course, it asks for 2dp, so you need 2 decimal places. And that's how to do the first part of this question, finding out the pH of a weak acid. And this is on the ionic product of water. And so these are fairly common calculations in acid and base. So let's get into it. Strontium is a group 2 element. Okay. That is obviously going to play a key role. Calculate the pH. So we're doing exactly what we did in the last part of the question. We're calculating the pH. Again, as I go through, I like to annotate. So you're going to write minus log, going to put the hydrogen ion concentration. So you know that you have to find that hydrogen ion concentration. Here is the concentration of a solution of strontium hydroxide. You may assume that strontium hydroxide completely dissociated in this solution. What does that mean? Well, that tells us that strontium hydroxide, now, as it's a group 2 element, I'm going to need 2. Notice I'm going to put a full arrow here, not reversible. This is going to break down into strontium 2+ ions, but it's also going to release 2 OH- ions. So you don't need to write this equation, but the whole point of this is so that you know, well, I've got 0.01 of strontium hydroxide, but for every strontium hydroxide that breaks down, you're going to have 0.0, well, you're doubling the concentration. For every strontium hydroxide molecule that dissociates fully, you're going to get 2 hydroxide ions. And we are told that the full strontium hydroxide, all of the molecules dissociate. So we're going to end up with a concentration of hydroxide ions that is 0.02. The next thing to do is you need to know about the ionic product of water. And the bit you need to know for A-level chemistry is that Kw, which is the ionic product of water, is equal to the hydrogen ion concentration multiplied by the hydroxide ion concentration. So your goal here is to find out the hydroxide ion concentration and then rearrange so that you can isolate the hydrogen ions and minus log to get the pH. So let's go ahead and do that now. How would you rearrange this equation to make hydrogen ions the subject? And of course, nice and easy, we're going to go Kw divided by the hydroxide ion concentration. Thankfully, that is going to give us this, and if you didn't spot earlier, you're going to lose a mark that strontium's in group 2 and that you needed to double it, then you will be dividing this by 0.01 instead of 0.02. So let's go ahead and put that in the calculator, and we want to write in 2.93 times 10 to the minus 15, and then we want to divide that by 0.02. And you're actually going to get 1.465 times 10 to the minus 13, but I've rounded it up. It's even easier if you just leave it in your calculator. Now we need to minus log our answer here, so minus log 1.47 times 10 to the minus 13, sorry, and that is going to give you your pH. I just had a sneezing attack. And that's going to give us a pH of 12.83. Again, let's do this to 2 decimal places. It's 12.8341, but as it's not greater than 5, we leave it as 12.83. And that is your pH. And does it make sense? You use your common sense check. Strontium hydroxide is a metal hydroxide, so it's obviously an alkali. That looks like an alkaline pH. All good. Let's move on. Okay, 4.3, the pH of barium hydroxide solution is lower at 50 than at 10 degrees. At 50 degrees, a 25 centimeter cube sample of this barium hydroxide solution was neutralized by 22.45 centimeters of hydrochloric acid added from a burette. So what they're saying is that we needed to add 24.5 centimeters of hydrochloric acid to neutralize 25 centimeters of the barium hydroxide. This question then goes on to say, deduce, which means work out, the volume of hydrochloric acid that should be added from a burette to neutralize another 25 centimeter sample of barium hydroxide, this time at 10 degrees. What would the amount be that's needed? Well, it's still going to be 22.45. And the reason being is that you're still using 25 centimeter cubed of the same barium hydroxide solution. So you have the same amount of moles of hydroxide ions that need to be neutralized. So we want to say same amount of moles of hydroxide ions need to be neutralized. Cool. So it doesn't matter the fact that we've changed the temperature, there are still the same amount of moles of hydroxide ions. We haven't changed that. Okay, let's move on. A buffer solution can be made from solutions of potassium hydroxide and ethanoic acid. Give an equation for the reaction between the potassium hydroxide and the ethanoic acid. State how this buffer solution resists changes in pH when a small amount of acid is added. Okay, so all we want to do here is how's a buffer solution made? Well, a buffer needs to contain, so just some notes. What is a buffer solution? A buffer needs to contain a weak acid and the salt of the weak acid. So essentially, we're going to carry out this reaction. We're going to add KOH, which is potassium hydroxide, and we're going to add that to ethanoic acid. So CH3COOH. What's going to happen is that's going to fully react. This is not, this is basically a neutralization reaction, so it's going to fully react, and we're going to get potassium ethanoate, which is the salt. Now, some people like to show the plus on the potassium and the minus on the salt there, but we can just leave it like this. You can show that if you like. And then we are going to get water, salt and water. And of course, that's what you get when you carry out neutralization. So that's going to give you a lot of this salt over here. So this is going to get you the mark for this part of the question, but this is going to give you lots of this ethanoic, potassium ethanoate, can't speak, and you want lots of that in your buffer because that's going to neutralize hydrogen ions. That's going to be able to react with a hydrogen ion. Okay. However, you won't have anything left to absorb hydroxide ions. So you need to get lots of the ethanoic acid as well. So what do? You add the ethanoic acid in excess. So what we want to do is react excess ethanoic acid with, sorry about the caps there, with potassium hydroxide. So you get potassium ethanoate and lots of ethanoic acid. To be honest, you want the salt of the acid and then you want excess of the acid. So I've put that answer in context of this situation, but actually your answer should be that you want excess acid reacted with the base so that you get a salt of the acid, and also you have excess of the weak acid available, and that is a buffer solution. You need lots of the weak acid, and that's to absorb hydroxide ions, and you need lots of the salt of the acid so that that can absorb hydrogen ions. So how does a buffer resist pH change? Well, it says here they want us to state how the buffer solution resists changes in pH when a small amount of acid is added. So when it adds a small amount of acid, in this particular situation, the CH3COO minus, so the ions of the salt react with hydrogen ions. I can't get a capital H going. Absorb hydrogen ions. So essentially the hydrogen ions get taken out. They cause a shift in the equilibrium, but really you want to just look at the ions of the salt. So if you were putting a more general one, not to this one, the ions of the salt absorb, hydrogen ions. And that's our answer. However, just in case you're being asked to explain how they absorb hydroxide ions as well as a little extra, the weak acid absorbs hydroxide ions. So if a buffer should be able to absorb hydroxide ions as well. So it can resist changes when you add a small amount of alkali or acid. But of course, this question is just focusing on the addition of a small amount of acid. Okay, let's move on. Okay, last part to this question, 4.5. A buffer solution is made by adding 2 grams of sodium hydroxide to 500 centimeter cubed of 1 mole per decimeter ethanoic acid. Calculate the pH of this buffer solution at 25 degrees. Give your answer to 2 decimal places. For ethanoic acid, the Ka is equal to 1.74 times 10 to the minus 5 mole per decimeter to the minus 3 at 25 degrees. Let's go. So what we're looking at here straight away, well, let's get into the equation first. What do you need to do? As usual, check it out, everyone. You're being asked with acids and bases, the most common thing, that is to calculate the pH. So once again, as a reminder, you need to remember where your minus button is, your log button, and you just need to minus log the hydrogen ion concentration. Now, there's an equation for buffers that you need to memorize, and it's just, you can look at why you rearrange it like this, but it's just easier to remember this. So let's start by actually writing the correct one. I'm going to just write the rearrangement, and that is that the hydrogen ion equation, concentration, I'm talking all over the place, is equal to Ka times the acid over the salt. So if you can remember that equation, hydrogen ion concentration is equal to the Ka of the acid over the salt. For buffers, you're absolutely sorted. Okay, the next step, there's one little further complication. We've been told that a buffer solution was made by reacting sodium hydroxide to 500 centimeter of 1 mole decimeter ethanoic acid solution. We have to remember that normally here the acid or the hydroxide, one of them is going to be in excess. So let's go on and find out how many moles we've got. And if we want to write the equation out, we can do. And the equation for this is NaOH plus CH3, which is the ethanoic acid, COOH. You might say to yourself, why not a reversible symbol? Well, this is a neutralization reaction. So one of these two bad boys, unless they're in the exact amount of moles, one of these, and it's a 1-to-1, we can see that one of these two bad boys is going to get completely wiped out. So we're going to get this. Now, that is going to react with the sodium ions. To be honest, you can get rid of those charges. You don't need to be putting those charges there, but I like to do it sometimes because it's the CH3COO minus ions that are important in our buffer solution, the ions of the salt. So remember, we've got alkali, acid, salt, and water, straight from GCSE. Okay, now, let's check it out. It says that we had 2 grams of sodium hydroxide at the start of this. And we know that we need to find the moles, basically. Stop waffling, Tom, and get on and find the moles. So we have mass over MR times moles. So to find the moles, I need to do mass over MR. That's 2 over 40. The 40 comes from the sodium hydroxide, and that equals 0.05 moles. So I have 0.05 moles of my sodium hydroxide right at the start of this. Okay, what's going to happen? Let's find out how much acid we've got. So 500 centimeters times 1 mole per decimeter. I need to convert them both to decimeters. The concentration is already in decimeters, but my volume isn't. So we're going to do 500 over 1,000. You remember how to convert centimeter cubed to decimeters. You divide by 1,000. That's going to give us our volume. Now, according to the equation, which is moles over C times V. You need to know that off by heart. You probably do from GCSE, that I need to do volume times the concentration, so times 1 mole dm minus 3. I'm going to get the moles of 0.5 moles, and that is of the ethanoic acid. Brilliant. So what we want to do now is write 0.5 there. When they react, look, I've actually only got, we can see there, I've only got enough to neutralize 0.05 moles. It's a 1-to-1, so I'm only going to neutralize 0.05 moles of the acid, which means I'm going to be left over with 0.45 moles of the acid. My sodium hydroxide is going to be completely out of it. It's been completely wiped out. I have none of that left in my buffer solution, but I do have 0.45 moles of ethanoic acid left. Well, obviously, initially there were 0 moles of these until the reaction took place. But once the reaction has taken place, how many moles of the salt do we make? Well, we go to our limiting reagent, which is the sodium hydroxide, 0.05. So I can only make 0.05 moles of the salt. Remember, this is the salt. This is the acid. All buffers need to contain, or acid buffers need to contain salt and acid. So now we just go back to our buffer equation over here, and we say, let's do acid over salt. So we're going to go 0.45 divided by 0.05, you're going to get 9. You're going to multiply that by the Ka, which is 1.74 times 10 to the minus 5, and you're going to get your hydrogen ion concentration. And your hydrogen ion concentration is going to be, let me just quickly work it out. I've got to plug this in the calculator. Oh my gosh, my calculator's off. 0.45 divided by 0.05 equals 9 multiplied by 1.74 times 10 to the minus 5 equals 1.56 times 10 to the minus 4. So you can round this to 1.57. This is pretty much, you can round this to 1.57 times 10 to the minus 4. But anyway, I'm just leaving it in my calculator like that. And that is my hydrogen ion concentration. So what do I want to do now? I want to minus log that answer. So I want to minus log, whack that in your calculator. Of course, you can just press minus log and then the answer button on your calculator. So we're going to go minus log answer equals, and you're going to get 3.80. So the pH is 3.80. Boom.
I can't handle the stress no more, dog. These damn A levels.